Right, good afternoon. I'm Pat McGrath. I'm a program director with ARPA-E, and welcome to the first fast pitch session for the ARPA-E Summit in 2015. So this is an opportunity to hear from some of the program directors and fellows on the ideas that we're thinking about and the programs that we're working on and what we're excited about right now. This is a little bit different than some of these sessions you may have come to in the past that these are actually much faster. So these are going to be 6-minute talks. And at 6 minutes, if the speaker is still going, they will be thrown off the stage. So it is going to be a little bit sharper, a little bit quicker, but there will be plenty of opportunity for questions at the end. In order to submit the questions, I believe those are the correct numbers. I'll look for a thumbs up, it is. So you can text questions or tweet questions to the numbers up on the screen. So this will be kind of a rapid fire discussion, and without further ado, I'm going to introduce our first speaker, Dr. Mike Haney, who's going to tell us about how microsystems technology can transform solar.
Thanks, Pat, and good afternoon, everybody. Solar cells, flat panel solar cells, like the ones shown here, have come down dramatically in price over the last couple years, and that's very good news. However, they're also reaching their limits, at least in the flat panel one-sun silicon variety, reaching their limits of harvesting efficiency. So the question is, how can we find a new technology path to transform flat panels? And as indicated here, we think we can do that with integrated micro-optics, which I'll describe. But I've added something to the title, a statement that there's plenty of room in the middle. So what do I mean by that? Well, when you think about technology pathways for photovoltaics, the foundation is nanotechnology, as shown here. We all know about nanotechnology. It's the foundation of many of our technologies. In this case, we can use band gap engineering and light trapping and other things at the atomic or wavelength scale to fairly efficiently harvest energy. But these have a harvesting efficiency of about 20%, maybe a little bit more, low cost, but a wide geographic and market domain. There's another path. If you can add macro technology to the nanotechnology in the form of, in this case, a concentrating lens, then you can get higher efficiency, but higher cost and more limited geographical and market domains. So the question is there another way, another path? And of course, the answer we think is yes. But before I say that, let's talk about the evolution of these technologies. A famous talk by Professor Richard Feynman in 1959 is credited with kicking off the nanotechnology revolution. His quote is, "There's plenty of room at the bottom," talking about atomic scale. A couple of years ago, Harry Atwater at the PVSC meeting took a twist on that, thinking about the system level approach he was taking in concentrated PV, and said there's plenty of room at the top. Very interesting. Well, the question is there a middle ground? And I think the answer is yes. Can we get the best of both worlds? Can we get the harvesting efficiency of concentrated PV and the flat panel and low cost of one-sun PV? And to do that, we want to get to the micro-scale domain, specifically doing integrated micro-CPV arrays. So we could, in principle, get harvesting efficiency of CPV, but the low cost and flat form factor. Now, this is a very rich domain. If you think about it, there are a lot of degrees of freedom at the micro scale, as I'll mention later, but you can think about different ways of concentrating the light, different ways of adding and combining currents and voltages. So you won't be surprised that my bottom line is there's plenty of room in the middle. So why do we think this is possible now? Well, if you think about it, microscale technology has already disrupted many markets. And I would claim that it is the engine behind most of technology market disruption. You think about computing, electronics, communications, wireless communications, fiber, photography, lighting, all enabled, all driven to disruption by microscale. Displays is a particularly germane one because it's achieved commodity level status here. You can buy a very complex system. During the holidays, I saw a 52-inch TV on sale for $220. But these are very complex devices. If you look at what's going on, they're thin film transistors and liquid crystals, but they're large area, on the order of 100 million square meters deployed in the US. Yet they've achieved commodity scale and the economies of scale that goes with that, and you can now get them for hundreds of dollars per meter squared. The complexity shown there is approximately the complexity we're proposing in the microscale concentrated PV. So that is the value proposition that we're after. New PV panel value proposition employing microscale technology to drive micro-concentrated PV to the same $100 per square meter. If we're successful in doing that and getting the performance, that will certainly transform flat panel displays. There's a lot of technical challenges to achieve that, so we recently published a couple of funding opportunity announcements under the name of Mosaic. I'll let you read it, but I hope you agree that it's a pretty clever acronym. And we published that in December, and we're now in the process of evaluating concept papers, and very exciting about this. So, to sum up, our goal is to take concentrated PV technology from the discrete domain to the integrated domain. Just as has happened with all those other technologies, it's time for photovoltaics to sort of get on the wagon, get on the bandwagon of microscale and leverage it. If you look at where we are now, Aminex is a good example. These are breadbox sized modules displayed in large panels the size of houses as shown there, and they work very well. There's already a trend toward miniaturization, best exemplified by, say, the Semprius technology, where now the lens modules are on the order of an inch or two, and now on the order of thousands of cells per square meter, but still in the discrete domain. Where we want to go is to the integrated domain, and that's the goal of Mosaic, to take advantage of the economies of scale and the complexity offered by the integration. And if we're successful, we'll even be able to go beyond, as other technologies, other applications have done with microscale. We don't know what the future will hold, but we're excited to think about it. So the bottom line is, we want to use or leverage microscale technology to fully unlock PV's nanoscale performance potential. And to get there, we want to take advantage of all that space in the middle. Thanks for your attention.
That's great.
Now for something completely different, I'm going to introduce James Klausner, the program director.
Okay, thank you. I have the privilege to manage one of the most exciting and interesting programs in ARPA-E that deals with the energy efficient and clean metal production and recycling of light metals. And why are we interested in that topic from ARPA-E? Well, if we could just replace the materials which we manufacture our vehicles and gain 30% increase in fuel efficiency, why wouldn't we do that? Well, of course, cost is a barrier. But we already see in the market light-weighted vehicles, such as the Ford F-150 is now a production vehicle, is a light-weighted vehicle. Of course, the Tesla Model S and the Boeing 787 are all light-weighted vehicles that have significant improvement in fuel economy. If we lightweighted our entire fleet of vehicles, there's 4 quads of energy savings to be gained by in fuel efficiency by lightweighting. And if you don't know, the nation consumes approximately 100 quads of energy per year. So that's about 4% impact on the total utilization of our energy. So why aren't we moving towards lightweighting vehicles? Well, steel is significantly less expensive and consumes significantly less energy in terms of producing steel. In addition, steel is much easier to recycle than light metals such as aluminum, magnesium, and titanium. So we have goals on primary production within our portfolio that we want to reduce the energy consumption, cost, and emissions associated with the production of these light metals, aluminum, magnesium, titanium, directly from ore to metal. And we want to get those so there's parity with steel for aluminum, magnesium, parity with stainless steel for titanium. So you have listed on this chart here all the wonderful projects that are going on in this program, and they all have booths that you can go and check out the excellent work that's going on from these organizations. And we're making a lot of interesting progress in this area. But for now, I'm going to focus on the recycling problem. If we take a vehicle and we shred the vehicle, it's basically broken down into a ferrous pile of scrap and a non-ferrous pile of scrap. The ferrous pile is easy to sort out. The non-ferrous pile is much more difficult, and there's mixed red metals and aluminum, magnesium, different alloys, and it's very difficult to recycle those because we don't have the effective technology to sort out those different metals. So what happens, we take that metal, we ship it overseas to China, India, and it's sorted by hand. So right there, just by taking that primary metal and shipping it overseas, we're losing the energy that it costs to make that metal, because now we're importing energy to replace that metal with primary metal. So one of the key considerations is, okay, if we move towards vehicle lightweighting, which we want to do, there's a number of different aluminum alloys that go into scrap. And I have a chart here, the source alloy and the sink alloy. Every block that's black, that source cannot go into making a sink alloy or making another alloy. Only the white spaces are where you can produce another alloy from the source alloy. So what happens if you look over on the right and you look at the flow of materials in terms of trying to recycle the scrap from these vehicles, you have a big sink of surplus metal that you can't use, which will probably get shipped overseas. And again, there's a loss of energy. So at ARPA-E, we're trying to develop new innovative technologies that will allow us to discriminate specific alloys so we can sort them out into their virgin metal class and reuse all of the scrap that we produce. So UHV Corporation has developed the world's most powerful linear X-ray tube, which will enable X-ray fluorescence detection of the metal using this X-ray source, fluorescing, and detectors of looking at the spectrum of the fluoresced X-ray source. And so they built a sorter. We're working with them to move this towards production. They have very interesting partnerships lined up, and I suggest you go visit their booth in the showcase. University of Utah has developed a variable frequency electrodynamic sorting machine, which is basically an eddy current machine where electric field induces an eddy current in the scrap pieces and is able to distinguish alloys. And they've built the highest frequency electrodynamic sorter. Again, they're going to have their instrument on display at the showcase. PARC, Palo Alto Research Center, has developed a hand sorter using electrochemical approach. It's the first time electrochemistry has been able to use to detect specific alloys. Energy research company ERCO has developed a in situ laser-induced breakdown spectroscopy probe that can go directly into a high temperature alloy melt and detect the exact elemental composition within that alloy melt to allow you to control what scrap you're putting in and what alloy you're producing from the recycling. So just to sum things up, ARPA-E is not only trying to tackle energy efficiency in primary production of light metals, but we also aim to close the loop in vehicle recycling and keep all our scrap metal in a continuous loop that we can continuously recycle. Thank you very much. And with that, go on to something new and introduce my esteemed colleague, Ramon Gonzalez.
Thank you, James. You see, you're counting the time here. It's 5:50, and I don't have my slides, so just reset that clock, please. How did I do? Okay. So you can see the question that these questions were sorted out, and then I just ended up with this question. I have to answer it now. The question that I have here at hand is, can biological conversion of methane, and for the purpose of this conversation, methane equals natural gas, can it facilitate small-scale deployment? The conversation here is based around a program that we have developed, that I led the development of, and currently is at the end of the first year. That is called Remote. I'm not going to talk much about the name. Let's break things down. Why is it that we're interested in natural gas? There's a couple of things here that most of you are familiar with, but just in case. We call these the age of natural gas because of the growth in production and use of natural gas, because of the growth in resources. And that graph there hopefully can illustrate the point very easily. So that's one reason. There's a lot of it. Why do we want to do conversion? Okay, because when you compare on the same energy basis the cost or the price of natural gas and gasoline, there's a significant spread in the price, as you can see there. It doesn't take very long for you to realize if you can turn one into the other one at high efficiency, you could be making a lot of money. So the question is, what is the challenge there? Why is it that people are not doing this already? I'm going to answer that in the next slide, but before I get there, I wanted to give you an example of this company, Sasol, which announced back in, almost 2 years ago that it was going to build a GTL, gas to liquids, plant in Louisiana, just to follow up, this is not, okay, very recently to say that, okay, we're not going to do it. Why is it that those type of things are happening? Why is it that people are not leveraging this price spread between these two and converting gas to liquids? The bottom line is on the basis of why we are using bioconversion anyway. So the bottom line is the existing technologies out there, these GTL type of technologies, are very high capex and operate at very large scale. If you look at the graph on the right hand side, what you have there is a picture at the top of a typical GTL plant. Most of you have been in New York, most of you have been in Central Park. So this one facility sits in a lot that is the size of Central Park. Hopefully that gives you the idea that this is humongous, it's big. Not only that, the investment, the capital expenses to build that facility is in the order of $20 to $30 billion. Not a lot of pockets out there can support that. A lot of risk involved in it. The graph to the left actually gives you a quantitative idea of how that goes. So it operates very large scale, very high capex. Why is it that we want to do bioconversion as an alternative to that? Exactly because bioconversion can operate at a small scale and is very capex efficient. Those are the blue points right there in that graph. You see that all of them are clustered to the left, low production, small scale, and low capex compared to the top one. And the picture down there shows you a picture of a typical corn ethanol plant, which is a typical bioconversion type of facility. When you look at on the same basis in terms of area, footprint is really determined if you want to deploy things at a smaller scale. Both of these technologies operate in the more or less the same scale when you normalize per unit of area. Based on the idea that there was an opportunity there for bioconversion, we developed a program within ARPA-E, and the program again is called Remote. This slide is a little bit technical. I'm not going to get into details about it. The bottom line is the program focuses on two areas: the development of biocatalysts and the development of reactors, processes that will leverage those biocatalysts. And that's what is reflected there, the top at the bottom. You're also going to see there specific numbers. Those are the metrics that we're using, the targets that we have for the program. So those targets are in energy and carbon efficiency, productivity, and capex. How did we determine that? Using a techno-economic analysis. I'm going to give you, in the next two slides, a little bit of a highlight about those, that techno-economic analysis. That in summary is going to tell you, if you hit these targets with our program, if we hit it, those technologies are going to be viable. It's not moving. Okay. This is the first one, and this is the numbers, essentially, techno-economic analysis. You have two graphs there. If you're familiar with the tornado plot, that's on the left-hand side. On the right-hand side is a break-even analysis. Bottom line, the left one is telling you, if you hit the parameters we're discussing, even if you talk about natural gas at $4, which is not there today, you'll be able to sell gasoline at about $1.50. So pretty appealing proposition. The one on the right says, don't panic about low prices in oil, because it's a matter of what is the price spread between the two of them. So you have two axes there. If you enter, for example, those two lines, if natural gas is at 3, as long as oil doesn't go below 60, you are fine. Today, this is Brent. Brent is about 59, natural gas is 2.5. So again, don't panic, no problem with that. So that's the economics of it. Same tool we have used for looking at the carbon footprint of these type of technologies. So that's reflected here in terms of total emissions. So the y-axis, total emissions, different resources in the x-axis. Our approach is the one that sits there with the two blue lines. You can see that in terms of total emissions, we sit on something that is equal or better than traditional or conventional oil. So 2 or 3 messages, take-home messages: CapEx, low CapEx, high efficiency, able to deploy at a small scale, is cost-effective, of course, and then you have an environmentally sound process. With that, that's the end of it. Thank you. Oh. I guess Pat is next, but he introduced himself already, so go for it, Pat.
So this will be a little bit of a change of pace. What we've heard so far are ongoing programs or programs that are just kicking off at ARPA-E. And what I'd like to talk about today is an idea that I've been looking at that I think there could be an exciting program opportunity. And I'd like to tell you about what I've been looking at, what I've been thinking about, actually with the hopes of hearing from some of you with ideas so that we perhaps could turn this into a program. So the topic that I put up is, can we have better catalysis without better catalysts? Now, that may be, to some of you, a ridiculous question. You may think that, of course not, that if you improve the catalytic performance, you have, by definition, improved the catalyst. So maybe a more precise title would be, can we exploit physical interactions to substantially improve activity and selectivity in catalytic systems without significantly altering the active site? That was a little bit over the word count, and I decided to go with something a little bit catchier. But let me tell you what my interest is. So we're talking here broadly about the area of catalysis. So this is to follow a bit on what Ramon was talking about. We are looking about ways of reducing the activation barrier in chemical transformations so that we can have chemical reactions go faster and have better controls over the products. In contrast to Ramon, I'm a little more interested in synthetic catalysts, and especially in heterogeneous catalysts. So looking at supported metals, metal oxides, any wide range of high surface area materials that can perform catalysis. Now, this is a $20 billion industry. From the energy standpoint, obviously, it's very important to fuel production, emissions cleanup and mitigation, energy conversion reactions. But it also touches every bit of our daily lives, from polymers to consumer products to agriculture to medical and pharmaceuticals. So as you might guess, for a very large market with a lot of applications, it's actually a very well-studied area. There's a lot of activity with a lot of brilliant people trying to find better ways to understand and improve active sites where reactions take place, where catalysis takes place. So just at a very high level summary of what some of those approaches might be, you can look at fundamental modeling to understand the energetics and the reaction pathways that take place in catalytic systems. There's ever improving techniques to tailor active sites to give us pristine control over reactions at the nanoscale and below. And there's also coming online ever improving high throughput methods where we can do combinatorial approaches to look at a vast array of possibilities of catalytic systems to achieve the reactions that we want. So it's fair to ask at this point, if we've got a very big space with a lot of very smart people working on it, what reason is there for ARPA-E to get in here? We typically don't get in to do research that's already very well covered. We look for new opportunities, and we look for what we call white space, ways of changing the field that are not currently covered. And I think there may be an opportunity here, and that's what I wanted to talk about today. So I think that there's a possibility that we can exploit physical interactions and mechanical energy to improve catalysis without necessarily improving the active site. So let me just tell you a little bit and a few examples from some work across the field that lead me to believe that this is a possibility. The first example, it shows a modeling study that looked at CO oxidation on a number of different surfaces. And what the study showed, unsurprisingly, was that at low coverage, platinum, palladium, the typical suspects, are your best catalysts. And what was interesting is that as we push the high coverage and start accounting for physical interactions taking place on the surface, we don't change the fact that platinum is our best catalyst, but we suddenly make nickel, which is a poor catalyst in a low coverage situation where physical interactions don't matter. Nickel is suddenly almost up on the same plateau as platinum. So nickel, which is 1,000 times cheaper than platinum, is suddenly not necessarily the best catalyst, but it is now in the range. So this is a situation where we have seen physical interactions can make a bad catalyst better. Now, even the authors would not claim that this model, this is a very simple model of the physical interactions. They won't claim that this is going to be a definitive and quantitative prediction of catalytic performance. But what's interesting is just how dramatically the physical interactions alter the landscape, alter the performance of these different surfaces. Carrying on the physical interactions, I'll look at another example where we have a zeolite system doing hydroconversion. And in this case, this is an experimental study that showed that when you go to a case of absorption compression, which is a case of extreme surface interactions, that you can have dramatic lateral pressures and a very large change in adsorption energies, you see a dramatic shift in the selectivity for hydroconversion in those catalysts. So you actually see a twofold improvement in selectivity for a C7 hydroconversion versus a C9, and that's not an easy thing to do. So it's another case where bringing in some interesting physical interactions gives you the opportunity to improve a catalyst just by operating in a different regime. One last example I have down at the bottom is NO oxidation, and this is a very interesting system in that it's entropically driven, and it doesn't even really fit with the cartoon of catalysis that we've been talking about. It has a negative apparent activation energy. But the study showed that even when you just put this in a porous substrate that has voids of the right size to stabilize the transition state, you can show a catalytic-like improvement. You can show catalysis simply by confinement, simply by physical interactions. And that's a case where you take something that's not even catalytic and use physical interactions to make it better. So this is just scratching the surface. There are other ways we could even get creative and think about ways of actively injecting these physical interactions. And this is at this point where my level of interest is I want to see, are there enough ideas out there that we can build a critical mass and build a program around this idea? How to exploit and make predictive systematic tools to make better catalysis without attacking the active site itself. So I'm getting beeped off. I couldn't even enforce on myself. So now the last speaker will be Dave Brown, who's going to tell us about another idea he's been interested in.
Hi, thank you all. So unlike the rest of the speakers here, I'm a fellow, and the role of the fellows at ARPA-E is to try and determine new areas for potential programs. And so this is a concept to take advantage of our husbandry of our natural resources to mitigate a big problem, which is greenhouse gases, and to do so in a way that's actually profitable. So how much does carbon capture cost? Well, you might say $50 per ton. That's a pretty standard number. I'd say that carbon capture is actually free. So I've got here a screenshot from a JPL visualization of CO2 over a year. Right now, this is May 1st. The red is high concentrations of carbon dioxide. On August 1st, it's all gone. What's happened over those 3 months is the growing season in the summer in the northern hemisphere. And if we look at the carbon levels over that same period, we see that in winter, when all that material is decomposing, there's a release of carbon dioxide, but in summer, there's actually a substantial decrease. And if you go through the numbers, you'll find that about 500%, 5 times US carbon emissions are actually captured every year by the plants. So the problem then isn't really the capture. They're fine at that. The problem is actually sequestering that carbon dioxide into a stable reservoir, for example, soil carbon. So what's happening to the carbon after it's absorbed by the plant? Well, about half of it is lost in respiration of the plant, and I'm not going to go into that further today. A further 80% is lost by microbiome respiration, and a further 20% is lost by disturbance and long-term microbial decomposition. Right now in the US, we're capturing and sequestering about 0.25 gigatons of carbon per year within our soil. To give you a sense, if you double that to 0.5 gigatons of carbon per year, that would be about equivalent to all transportation CO2 emissions in the United States. So that's equivalent to taking every car out of the road, off the road, and every plane out of the sky. So what motivates this as a possibly economical program is the fact that improved soil is worth money. Right now, according to the USDA, as in what they will pay out to farmers who are practicing low erosion tillage practices, is topsoil is worth $28 per ton. Topsoil is high in organic carbon. Good soil leads to higher yields, better fertilizer efficiency, which decreases the amount of nitrous being emitted, and also improves the water efficiency. If you look at these two maps, on top top is where we grow our highest yielding crop, corn in the United States. On bottom is where soil carbon varies, and the red is the most rich area, and there's a great overlap there. So the challenge then is engineering that soil sequestration. I think of this as with a toy formula. The amount of carbon sequestered is equal to the product of two things: the amount of biomass going in of a type times the portion of that that's stabilized. So there are two strategies that you can focus on, which refer to the two parts of this equation. You can look at how much biomass is coming in. Right now that's about 5 gigatons of carbon per year in the US. And focus on the roots, which are the most stabilized portion of that of the degrading biomass. So if you can improve the mass and spread of the roots, you can increase the amount that is going in to the microbiome to be stabilized. The second is you can try to actually engineer the microbiome that is either decomposing or stabilizing the carbon into either CO2 or more complex carbons, which will remain in the soil for many, many years. In order to do this, you need to develop some tools. Enabling technologies that I would consider and be really interested in hearing about from you, the audience, after the talk, is, first of all, actually we need to measure the size, biomass, and distribution of roots underground, which is a difficult task because the roots are, as I said, underground. We need to do analysis, especially with the second approach, of the microbiome. We need to understand what are the various soil populations and how are they being affected by our engineering approaches. And we also need to have rapid ability to measure the carbon, the quantity in the soil, the carbon quantity in the plants, and how it is partitioned into different chemical types. And all of this, in order to ensure rapid deployment, needs to be integral into the field units that already roll over our nation's forests and our agricultural fields. So that's harvesters for trees or combines for agriculture. So overall, the idea of this program is that we can make a substantial impact if we can retrofit carbon sequestration onto our existing network of agricultural growth and forests. What we utilize is the existing logistical network, which would hopefully allow the cost of such a program to be very low. We would then also use the fact that there is already a nationwide distribution system for seeds and for saplings, which could be retrofitted through biotechnology and genetic engineering. And at the end of this, what we are actually creating is a remediation of the soil. That's a valuable agricultural commodity which will economically drive the implementation of the program and allow the offsetting of the transportation emissions. And so with that, I'd like to thank you all and give the floor back to Pat for the question round.
Thanks, Dave. So at this point, if any of you do have questions, please do text or tweet to what's up on the screen there. We do have a couple of questions that come in, and actually the first one will go to you, Dave. That's paraphrase most of these, but what plant species are you interested in?
So as of now, this is a potential program, so we don't have a particular species that is picked. We are, of course, looking primarily at bioenergy crops and primarily at perennials, such as miscanthus or poplar, which have deeper root networks than annual crops.
Okay, thanks. Next question will be for James, and this is actually going back to the beginning of your talk, but what is the additional cost for lightweighting a production vehicle?
That can't be addressed specifically because cost information is proprietary. But what we can do is we can look at a Ford F-150, which is a production vehicle, and look at the steel version and the lightweighted aluminum alloy version. The lightweighted version is only just less than $400 more than the steel version. So from a consumer point of view, to get an extra 20 to 30 miles improvement in gas mileage for just under $400 more for the vehicle. Substantial value proposition for the consumer. So we do expect significantly more lightweighted vehicles to come on the market in the near future.
Okay. So rolling on, and Ramon, there's one that did come in for you. Let's see. What do you think are the best near-term deployment opportunities for methane bioconversion?
Certainly there are opportunities for, in the context of the program, for resources that are more remote. We define those as being either too far from the market or too small for the deployment of more large-scale type of technologies. So you can think about flare gas or associated gas, for example. Even offshore type of opportunities. I think those are the primary targets I would think about.
Okay. So I'll take one in from myself, actually, and it's the question, again, paraphrasing, is how do you know if you target physical interactions that you can improve good catalysts and not just bad ones? That's actually that's a pretty good question. So the examples that I ran through were modeling studies and pretty early research, and I'm not trying to make the claim that by looking at physical interactions that we're going to not need improvements in active sites. What I'm interested in finding is, can we find new tools that enhance the work that we're doing in catalysis? What we've seen in some of those examples is that there are areas where physical interactions, or even some other, when you look at the work on ball milling, that mechanical energy can actually have more of an effect than the quality of the active site. And that's compelling, but that doesn't necessarily mean that's a universal case. But what I would be looking for in a program to see that there would be an ARPA-E opportunity is there a systematic way that we can look for new regimes to operate, look for new ways of seeding and exploiting physical interactions, that we get the same kinds of effects that you get in major improvements to catalytic systems. So let's see. Got one, just to get through everyone before we do our second round for others who've already gone. Mike, if you succeed, how will you be able to expand the markets? Let's see, no, let's actually start that over here. How will the new microscale solar PV panels be able to get into solar markets?
Oh, sure, certainly. Well, if you think about it, there's two ways to impact the solar panel market. One is to enhance existing markets in residential, commercial, utility. You could, for instance, expand those markets. If we achieve 50% more harvested energy per dollar, you could imagine a geographic expansion where CPV, concentrated PV, could expand out of the desert Southwest into other regions. And that's certainly a key thing to think about. But also, what's even a little more exciting is to think about a demographic expansion of the markets, where now if you have that enhanced efficiency, harvesting efficiency, you can think about expanding the rooftop market to roofs that would never consider them before because they're too small now. So we could go into smaller roofs, and that would be a demographic expansion. So I think that would be exciting as well.
One more for Dave, actually. So one question coming in. What research is already out there on boosting soil sequestration of CO2? What do we already know?
So we have some good understanding that conservation tillage practices improve the soil sequestration. We have a good understanding that root biomass increase leads to soil sequestration. We don't have a strong idea of how to engineer the microbiome, though we do have some people who are just now publishing results where they're able to actually, by altering the plant, manipulate the microbiome populations, or get change, in one case, which ectomycorrhizal fungi is symbiotic with a poplar tree.
Okay. Then now one more for Ramon coming in. Is the remote program interested in conversion of methane to chemicals, or are you exclusively looking at fuels?
Yeah, so in the specific cases of the projects that are funded through the program, there is a mix of both. Actually, most molecules that we have as targets have a dual market type of application, so we're looking after alcohols, acids, lipids, and hydrocarbons. So those are molecules that would have applications both in the chemical and the fuel market. Our final goal, not just as a program, but as an agency, is fuels, is energy. But we do recognize that the first market opportunities are going to be on the chemical space, because you can fetch a higher price and can enter the market and then leverage that to produce a fuel.
Okay. One more back for James, actually. And it's asking what level of interest you've had from auto manufacturers on the metals technologies.
Oh, I think there's...
Actually, I'm going to go ahead and make that a more general question. What level of interest do you have from industry on the metals technology?
So I think if you look at every major car manufacturer has a lightweighting division within the company. I think there's a significant movement in the industrial space gearing up production of lightweighted alloys for vehicles. Especially stamping facilities that need special processes to handle aluminum, magnesium alloys, which tend to be more brittle. So also the melters are looking at, really interested in new recycling technologies so they can pull back the scrap and reuse the scrap towards these vehicles. So there's an infrastructure in place that's evolving as we speak, and where it goes is really going to depend on the level of technology we have to enable the development of those products.
So got one that came in for me, somewhat taking me to task for maybe narrowing my search too much, asking if I'm interested in using physical interactions to improve catalysis in biological systems as well. So the honest answer is at this stage, that's not something that I'm interested in, but that doesn't mean at this stage, pre-workshop, I'm open to be convinced that I need to expand my scope. So what I'm looking for at this stage is the best ideas that I can shape a program around. And if the challenges are appropriate for the time and funding levels that you get in an ARPA-E program, that we could make a push not only in heterogeneous catalysis, but also perhaps in enzymes. That's certainly a possibility, and I'd be open to having that discussion as part of a workshop. My concern is that the challenge is when we talk about homogeneous catalysis in general and enzymes in particular, the physical interactions and the degrees of freedom are quite different in a biological system than what you have in a heterogeneous system. And actually, I'd like to throw this back at Professor Gonzalez to see if he has any thoughts on heterogeneous catalysis versus the biological conversion routes.
No, I agree that there's a significant number of differences there. There are huge challenges on the bio side. We think about enzymatic catalysis. That would be the real question there. Mm-hmm. I think there are great opportunities there, but you're completely right. You cannot put all your eggs in one basket, but you don't want to have too many baskets either, because you don't want to have enough eggs.
I guess maybe the question is, do I want to pitch two programs? Question for Mike, could the micro-PV technology also apply to other sectors besides PV? So where else could this technology go?
Well, I suppose the question is about micro-concentrated energy. I'm not sure. Well, micro-scale technology certainly...
Somebody wants to tweet a clarification. If I bungled your question, please go ahead.
Yeah, well, I think I did mention that micro-scale technology is the engine by which trillions of dollars of disruption to the market has happened. My main point, I think, was that PV needs to get on that wagon, and we're actually behind, and it's an opportunity we should take. But specifically, if you think about photography, with similar lens kinds of structures, lighting, where within a decade, a 100-year incumbent, incandescent light bulbs are going to be displaced by a microscale LED technology. So I think there are many applications for microscale technology in general, and microphotonic, micro-optical technology in general as well.
One more for Dave, your popular one here. This is a pretty simple factual question, but how much total carbon could be stored in U.S. soils? So a difference from what we're doing today to what the maximum.
Yeah, so that's actually still a question that we don't know the upper limit. I think given that we know that there's some high carbon, low carbon soils in the US, we could anticipate that we could put probably another 50 gigatons of carbon within the US, which is 100 years of mitigation. The upper limit though is unclear.
Okay, and then follow-on question to that is because you mentioned topsoil is that there's an economic benefit. What's the size of that market relative to the carbon capture opportunity?
That's an interesting question. So on the order of like 500 million acres that have low carbon soil that would need to be remediated, particularly in the southeast. So that's fairly large. If you imagine that you have a 10% increase in yield, which $40, like $50 billion market probably pretty easily, if it works, if it really, really works.
Okay. Let's see. Got one more for me, and this is another one asking for other possibilities for catalysis, and this is a question of whether a plasma could actually replace traditional catalysts. Somewhat interesting because another program that I've involved in involves plasma research for fusion, but this is a little bit lower temperature. So the answer to that is that there's quite a bit of work in plasma reforming, especially. So that's an active field of work, and it's certainly a possibility. Learning the scalability and costs of that would be the challenge that I'd be most interested in seeing. Question for Ramon, and this comes really to an industry perspective. So the question is, how do the major energy companies view traditional GTL, the large scale versus?
Can you repeat how?
How do the major energy companies view the small scale bio GTL versus the mainline large scale GTL?
Yeah, so GTL is a hard business to be in. So after I set up the program, I have been attending GTL conferences. I think I have spoke in about 4 of those over the last year or so. Is really a foreign concept today. This bio GTL is a foreign concept to the GTL community. The community itself is very receptive. They have been struggling for years and years of not being able to have commercial success in that area, so they're pretty open to new technologies. I get a lot of positive feedback, but remember us as ARPA-E, we are very early on the development cycle, so it's going to take a few years before we get out there. But it's a very receptive community. They're looking for opportunities that would really make these happen, and these is converting natural gas to liquids.
Okay, so we have about 10 minutes left here, and there are a few questions coming, but I think we will have time for more, so if anybody still has a question they'd like to get in under the gun, there should be time. So that number is up there on the screen. I did have a question that came in for James, actually. It was a question between the recycling portion of metals versus new production. What is the energy impact for what we're currently shipping overseas for recycling? What is the footprint there relative to new production?
So if you look at the amount of metal that we ship overseas and look at the energy that was required to extract that metal from ore, assuming that metal came from ore, it's probably about a 0.4 to 0.5 quad impact. And that's just with current vehicles. ARPA-E's mission is to try and look into the future and anticipate problems and develop technologies that are able to solve problems before they happen. And if we have a significant amount of our fleet being lightweighted, you can anticipate 7 years from now being able to reuse that metal is going to be a much bigger problem than it is today, because the significantly more light metal going into the vehicle that needs to go through recycling. So it's more of a future problem that we're trying to address today.
Okay. There's one actually fairly broad question that I can't answer in detail, but the question basically says we covered 3 programs up here that are ongoing, or one that is just in the solicitation phase. And the question is ARPA-E interested in ideas under those programs, under the open call? So one thing I just want to make clear that, and this applies across the summit, the open solicitation is out there. I encourage all of you to read it, but that's about the limit of what I can say about that solicitation. Now, in terms of any other ideas, if you have something that you believe is relevant to any of the programs that you've heard, please come find us after the session. We're always interested to talk to people and talk about good new ideas. And it is hard to say what the next step would be after that, but there are mechanisms that we can find new ways of working with you if your idea really will strengthen a program. One more question for James. So what of the technologies that you discussed, what is your view as far as what's close to commercialization? So specifically this is recycling or the new builds?
Actually, all 4 of the recycling diagnostic technologies that I put up, they're all fairly close to commercialization, and all of those have been demonstrated to be efficacious in terms of identifying specific alloys of interest. And all of those have strategic partners, and the next phase is building prototypes and putting those prototypes out into a industrial setting and testing their durability and their throughput into an industrial setting. So we're very optimistic that within the next 2 years we can get those into production.
Interesting one here for Dave, and this is an interesting question. Are there farmers anywhere being paid for carbon sequestration, and if so, how much?
No.
Okay.
No, there aren't.
That was an easy one. So one for me, have you considered approaches to managing conversion and selectivity through separation and recycle? And this is a good question from presumably a chemical engineer in the audience. And actually I appreciate it. So one way that I've been looking about the possibility of exploiting physical interactions, of finding new ways of enhancing catalytic activity, it's very similar to process intensification approaches that are out there that look for ways of modifying the transport in large-scale reactors or in unit operations to increase the throughput, increase the productivity. What I'm advocating is actually a chance of doing process intensification all the way down at the where the reaction actually takes place. So it's really process intensification for the reaction itself. Now that itself doesn't actually answer the question that came in. Is that in any way superior to improved separations or reactor or process flow design? And frankly, that's a challenge that any process has to answer, that you could come up with a new catalyst through any number of ways, but ultimately for that to matter, you need to prove that using that catalyst is better than simply taking what we have and getting a better reactor design. So I think that would be a challenge over the long term for a program to prove that these new tools, this new way of improving catalytic activity is better than just good reactor design, and the hope would be that the answer is yes. Question for Mike: what process cost impacts do you anticipate from micro PV versus current technology?
It's a very good question. The way we've been looking at this is sort of through a bill of materials approach, where if you compare, for instance, flat panel TVs to what we anticipate would happen with a micro CPV approach, it would take years for the market to drive down the cost to the hundreds of dollars a square meter. But in principle, you begin with the balance of materials. If you do some, and there have been some preliminary balance of materials analyses done, and so obviously you have the PV material itself, and by using concentration, and if you know how to pixelate them, you can save there. But in the optics, it turns out you have some scaling benefits of making the lenses very small, so the mass, the physical mass of your optics is small. And if you are using polycarbonate, for instance, as your material, you can make a direct calculation of how much you need. I think that answers the question. I think the approach to achieving the hundreds of dollars per square meter, maybe $100 per square meter, will be based on achieving the economies of scale similar to what we have in the flat panel display, which has gone from $1,000 a square meter to a couple $100 a square meter in the last decade.
Okay. So we are at the 5-minute mark, so we have actually only one question left in the queue. So if you have anything burning right now, please get it in. We've got 5 minutes to go. And we'll have one more question for Dave. And the question is, might there be other benefits for farmers in engineering their crops for higher CO2 sequestration? One example given would be higher crop yields.
Might there be other benefits
for farmers in engineering the crops for higher CO2 sequestration?
Yeah. Well, if you get more carbon in the soil, you should be able to improve your fertilizer efficiency. And that would decrease the costs for farming the land. You would also improve your water efficiency, and that's a major problem for especially farmers out in the Great Plains and the west of the United States.
Question, and one more for Ramon now. So in the remote program, what have you demonstrated thus far, and what will you demonstrate by the end of the program relative to the still small scale, but the production that you alluded to in the slides?
Yeah, so the product, you guys remember I said there's two general areas. One is for the biocatalyst itself, and the other one is for the reactor or the process. The guys working in the catalyst, that's going to be very small scale. So engineer organisms that are able to do what we are setting there as target metrics in terms of carbon and energy efficiency and kinetics. The ones on the process side, it's about 1/3 of the program, a little bit more than that in terms of investment, but 1/3 of the projects. Those are having prototypes that are a little bit larger, so hundreds of liters in terms of reactors and so on. So it depends on what area of the program. The scale is going to be different and the targets are different. All of them geared towards the metrics that I gave you that would enable that type of economics that I highlighted there.
Okay, thanks. And I think this may be the last question here, and it's, Dave, you're popular. You're increasing storage, but what about long-term cycling? Will it come back out to the atmosphere eventually?
I think if you wisely manage the land, you will be able to mitigate that. One thing we've been thinking about a bit is, are there technologies we could implement in forest land after it burns, so after a forest fire where there's significant loss of carbon. And so you can think of remediation strategies for that as well. Obviously, if the earth cools, increases in temperature a significant amount, you start to worry about loss of carbon in lands that become less arable, and that it being burnt off, especially in the southern Great Plains.
Okay. And with that, we've got a minute to go. So with that, I'm actually out of questions here. So I am ready to wrap up unless somebody gets something in the next 15 seconds. I'd like to thank everyone for coming and hearing our thoughts. And like I said in my talk, and for all of the speakers, we're interested in hearing from you. So whether it's an ongoing program or something that we're just starting to look at, the reason that we're here talking to you, the reason that we hold the summit is to hear from the community and hear from new communities. So if anything really piqued your interest, or you think there's something that we need to hear about, please find us. We're here all week. So I'd like to thank all of the speakers. I'd like to thank all of you for joining us. And thanks for joining us in here and kicking off the summit this way. So I hope you enjoy the rest of the week. And also, there are other PDs in the room. Their fast pitch sessions will be coming up at 3:15, I believe. Is that correct? 3:15. So you got 15 minutes. We got another round of this going on. So please enjoy. Thank you.